So we're basically doing our EFA portion of our homework assignment today. That's not going to have to be turned in. We're just going to be grading the PCA part and then the write-up, the concluding kind of questions. So upload those to Blackboard by 11 p.m. on Thursday. And let me know if you have any questions. I have office hours right after class.
All right, so to pick up where we left off Tuesday, we did our first factor analysis just using the FA function. The only difference between the factor analysis function and the principal functions is we add this, the factoring method, FM, and in this case we put PA for we wanted the principal axis factoring. And then once we ran that, I believe we stopped here at this communalities table. And as a reminder, like as far as running this, you don't need to worry about what it's doing. That's just how we got this, what SPSS would output with that initial column as well as the extracted communalities. Did we get into answering A, B, and C, or did we stop here? Or do we want to discuss A, B, and C?
My recollection is that we did not get to that.
Okay. So what is the difference between this communalities table versus the ones that we've looked at earlier in our lessons? Anyone at all?
Got some good information in the chat here.
There we go. Yeah, so I'm seeing several answers popping in here, and yeah, the if you remember when we did the principal components analysis, that initial was just one for all of them. It uses all the variants, which isn't the case when we have a factor analysis. So which variable has the most in common with the other variables in this data set? Seeing, yep, Casey and Stephanie say in DEP 104, and we can see that its communality 0.724, which is pretty substantially higher than the rest of them.
Well, and to be clear, the overlap is the first column, and then the extracted is the second column. So DEP 104's overlap with the existing variables is it shares 53.3% of its variance with all the other variables in the analysis. And of that amount that it put in, of the 53%, it got back almost a quarter of it from the extracted factors. So 72.4%.
And then the least there we go. Yeah. The scrim 102 here was 0.075. For our eigenvalues, the way that we call those from our factor analysis, which was FA4, there is if you do use your dollar sign, you have these values, and that again, it will print all of the eigenvalues, but keep in mind that we only extracted 4 values, and so if you wanted, you could add brackets and say give us 1 through 4, and it will just give us those 4 eigenvalues for our extracted factors. And by the way, I updated the Google Docs to add in the code that we'll be using today. So if you need it, it's in there. So once again, the values portion of FA4 is those eigenvalues, and we can call the 4 eigenvalues from our extracted factors by subsetting using those brackets and just indicating 1 through 4. For what variance is being, in the original, is being explained by each factor, we can look at our PSYC output, just like we've done before, but putting in FA4, round to 3 digits, and we'll go ahead and use our cut of 0.32. And this is going to give us a lot of information.
Throw in the chat a thumbs up or a yes when you've managed to run this before we go through it, because there's a lot of output. And while you're running it and throwing your yes in the chat, one thing I want to point out about eigenvalues and factor analysis is that they all tend to be smaller than the ones in PCA. And that's partly because it's not 100% of the X variance that gets thrown into the analysis. So if you'll notice, we extracted 4 factors, but the last 2 eigenvalues were smaller than 1. But that's not because that doesn't mean we over extracted. The eigenvalues in EFA run on the smaller side than PCA. And that's why you want to always use the parallel analysis or minimum average partial in order to figure out the extraction. So it looks like we're probably good to go on reading through the output here. Thanks, everyone.
All right, so if we're looking at the explained variance by each factors, we're going to come back to this table that we've looked at before. And Anna, do you want to take us through B and C here?
Sure. So B says, what was the variance in the original variables that was being explained by each factor? So we got the eigenvalues, we've got the variance in the original variables being explained by each factor. You're going to look at your proportion variance line. So the first factor explains what proportion of variance in the X variables.
%.
Yeah, 11.9. Yep, 12%, 11.9% exactly. And so the second one is 11.7% and so on. That's where you answer items 28B. But then the next row tells you the cumulative variance, how much total variance is being explained by the extracted factors. And again, in EFA, you're always going to see a reduced amount compared to PCA because EFA doesn't put in all its variance into the analysis. It only puts in shared variance. So in total, how much of the variance in the X variables do our 4 factors cumulatively explain? Yep, Linda's got it. We're at almost 40%, 39.8%. Yep, perfect.
All right. Everybody good there? So for this next bit, we're looking at that. If you recall, we pulled up our residual correlation matrices before, and looking at what percentage of those have an absolute value of greater than 0.05. So I'm just going to copy in a chunk of code here, and then we'll decompose it and look at what each piece does. So starting with FA4 residual, that's where we're actually calling that residual correlation matrix from our factor analysis, wrapping that in absolute value just to get rid of those negatives and take the absolute value.
A quick insertion here. What does residual mean when you're talking with stats? Can someone just tell me what, when you hear the term residual, what should you be thinking of in like regular, normal English? Good. Error, exactly. Error leftover. So this matrix, the residual matrix, what does it represent? So Josh says it's a matrix of error, but what kind of error, right? What are error in what? Do we want to walk through this a little bit again? I know we covered it in lab and when we did our PCA, but it's worth repeating probably. Okay. When we start off with our variables, in this case we have 16x variables, if we just asked for a correlation matrix, that correlation matrix represents the association or overlapping variance between each x variable and every other x variable. When we do PCA or EFA, we're taking 16 variables and we are reducing it down to a smaller number of components or factors. So by definition, because the method is parsimonious and it's reducing the amount of information, then we don't get 100% of the information back. So we started off with 16 variables, we ended up with 4 factors. Obviously, when we have 4 factors instead of 16 variables, we've lost some information. So the reproduced correlation matrix is the estimated correlations with the reduced amount of information. So if I only have 4 factors, what is my best guess about how x1 correlates with x2, x1 with x3, x1 with x4, and so forth? And those correlations are not perfect because they're based on less information. So that's the reduced correlation matrix. There's the real correlation matrix, there's the reduced one, which are the estimates based on the extracted information. If I subtract the reproduced correlation matrix from the actual correlation matrix, then I get the residual correlation matrix. And so the residual correlation matrix is one of the ways that we can tell how effective is our PCA or EFA, because we don't have a t-test or a t-test or a p-value or anything to know the quality of our factor analysis. We have to use these indirect methods. And what we're looking for is to make few large errors. We want the residuals to be small so that the difference between our estimated correlation and the actual correlation is below 0.05 as an absolute value of a correlation, not a p-value.
Yeah, and if you want to go back, number 9 is where before we did this like piece by piece, where we looked at the correlation, manually computed it, and then calculated the difference, and then looked at those residual things to see that difference was 0.18. So if you want to go back and look at number 9, that's where you'll find that. So what we had here so far, once again, looking at those absolute values, when we wrap it in the lower matrix and say digits is 3, we just get that bottom triangle. And then if we turn that into a logical statement to see how many of those are greater than 0.05, we'll see that there are 7 of them that are greater than 0.05. Then just divide that by the length, multiply it by 100, and we get 5.83%. So 7 of our variables for 5.8% of our values in that residual correlation matrix are greater than 0.05. And how does that compare with that PCA equivalent? If we scroll back up here, we had 35.6% of the original one back up in number 9.
So in the original PCA, as Morgan pointed out, there was a lot, there were many more of the residual correlations that exceeded 0.05. So we were off in our estimate a lot more in a PCA than we are in an EFA. And that's pretty much always going to happen. But that's because EFA doesn't put in unique variance. And because it doesn't put in variance, we have much faithful ability to estimate the intercorrelations among variables. So it's one of the ways that we can really make a lot fewer mistakes by using EFA.
Any questions before we move on? So for number 30, all we're doing is we're copying and pasting. We're going to do another factor analysis, same as this one, except now we're going to not use a rotation. So all we have to do is change our rotate to none. And I'm going to store this as fa4.none. And so if we want to look at how many variables have complex loadings, what function might we use? Yep. Morgan says print PSYC. We'll set that cut to 0.32. And then take a look to see how many complex loadings we have.
I think we have like 7.
I think you're right.
And then 2 of them are very complex.
So we've got Scrim 103 here, SE 101, SE 102, SE 109, 110, DEP 101, and 104. And for our rotated matrix, we'll go back and reprint the FA4, which was the first factor analysis that we did. And in this rotated one, how many variables have complex loadings?
It looks like none of them.
Exactly. And then, are there any that don't load on any factors?
I don't think so.
So we've got a nice simple solution here. As far as which variables load highest on each factor, that's pretty straightforward. Marker variables, just as a reminder, what are we looking for marker variables?
above 0.6 and they're simple.
Exactly. So looking at all these, they're all simple. None of them are complexly loaded. So any of them that are above 0.6 is going to be a marker variable. And then for how you would name each factor, that's where we're going back. We're looking at our data dictionary to see what is SE101 through SE107 versus 108 through 110. Give it some sort of label. That's all pretty straightforward.
Before we move on to the next one, so Morgan asked whether the rotated EFA is easier than PCA, and the answer is, if you look at our best option PCA, I'm pretty sure you're going to find that it lines up with this EFA almost identically. So the reason why we like EFA is because we are kind of only getting the overlap in variance. We're not throwing in the uniqueness of variables. And to the extent that psychological constructs, we think, don't exist in like a way that we can directly measure them, we need to indirectly measure them. We like variables that overlap with each other because we think that the area of overlap is where the purest measure of that psychological construct is. So for example, working memory is not something you can directly measure, but you can assess it by asking people to do things like how many correct they get on an NBAC test, or how many digits can they recall forward or backward, or things like that. But that's not a pure measure of working memory. And so if you were to overlap the number corrective, how long of a string of digits can you memorize, how well did you do, how many correct responses did you give on an NBAC test, and so forth, that overlapping variance is where we think the purest measure of that construct is. So that's, we also like EFA because, as you'll see when we move now into path analysis and then structural equation modeling, this is the way we best index error-free measurement of psychological constructs. But for purely exploratory reasons, PC and EFA give you almost identical responses. They're just conceptually different, as we've talked about in class. So before we move on to the last part, where we're actually, now we have subscale scores. And so typically at this point, you would work to calculate an alpha coefficient to look at the internal reliability of the variables that load onto each component or factor. So that's the last thing we're going to do. But before we do that, when we first started this assignment, this is back when we still went to class. I think it was one of you, maybe Josh, who said, I don't quite get what we're doing. I don't quite understand what EFA and PCA are doing. And we talked about how this was really experiential. It was important to just get in there, play with data, do it a bunch of times, try different things, try different extractions, different rotations, PCA, EFA. And so what I want to know from you all is if you feel like this is starting to make sense. Do you feel comfortable with the idea behind what we're doing?
And on that, I'd really recommend, now that we have finished all of the PCA and factor analysis, I would strongly recommend that everybody go back through and run through your script again, so that you can, all in one sitting, see like, all right, this is when we did this rotation, when we did this rotation, when we did no rotation, when we did this number of factors, and really look through it and try to synthesize all those differences and such, and that will really help kind of make it all clear when you're comparing them all directly instead of broken across 3 or 4 weeks.
Excellent. I'm super glad to hear this, you guys. And Austin's advice is a really, really good one. We've been stretching it out, which is important, so you all get it, but it will be nice to say like, okay, what happened when I only did 3? Oh, look, I got more complexly loaded variables. What happened when I did 5? Oh, look, I had a factor that was only defined by one item. What happened if I did a oblique rotation? What happened when I did an orthogonal rotation? That kind of stuff.
All right, so then
just a final reminder, since Morgan threw it in the chat, and it's really an important one. Morgan, you're absolutely right that from a mathematical perspective, EFA and PCA are basically identical. The reason why you would choose one over the other has everything to do with theory, whether you're talking about the idea that there is this, like, say, construct, and it is driving how people perform on specific items. So if you believe, for example, that human beings actually have working memory, that it's a thing, and that different people have different amounts of it, then if I'm pretty good at working memory, I should be good at a bunch of tasks that are supposed to measure it, like digit span or NBAC or go, no go, or whatever. If I think I'm bad at working memory because it's a thing that actually exists, then I should be bad at all those tasks. If instead, that's EFA. If instead you think there is no such thing as working memory, we just have, for some reason people say buy certain kinds of cereal, and I just want to figure out why they buy it, and I don't give a shit about whether there's a construct around attractiveness or desirability or something, and I'm just going to maximize the overlap, right, the parsimony of my data, then I would use a PCA. And when we start talking about factor analysis, then it will make a lot more sense, because I'll show you in pictures sort of conceptually what's the difference between PCA and EFA. Good.
All right. So moving into Chromevox Alpha, where we're looking at the internal reliability of the separate items. So here for Descrim, we've got Descrim 101, 2, 3, and 5. And we're creating some Descrim score based on the scores from these for variables, but that leads us to a question of, well, do these items actually hang together? As Anna was just saying, like, you could think of this as being, the NBAC and the digit span and like 4 separate tasks that you would think that, being high on one should be high on the others, being low should be low on the others. But if you're looking at these 4 items and somebody's high on Descrim 101 and 102 but low on 103 and in the middle on 105, then it's a question of, are they really capturing the same thing? So we'll use the alpha function from the PSYC package, and all we're going to do, we'll select from PCA DF2. We're just going to select Descrim 101 through 103 and 105. So just as a reminder of what that select function is doing, all it's doing is pulling out those 4 variables. And then when we wrap it in alpha, we get our reliability analysis. Now, when you look at the reliability analysis output, you're looking at a few things. First of all, up here at the top, here's where you're getting your alpha from. So the alpha for this Descrim factor is 0.54, which is garbage by our standards in psychology. The other things that you'll look into from this output, it has this section here called reliability if an item is dropped. So this is saying our reliability is 0.54. If we removed Descrim 101 from these 4, then the reliability would drop to 0.43. If we remove Descrim 102, it's going to be 0.53. Descrim 105, remove that, and our alpha would be even lower with 0.47, etc. So if you're looking at these, and for instance, say our alpha is 0.54, but if this said, oh, if you remove Descrim 102, that alpha is going to be 0.83, then you know that, like, okay, this one item in particular is really screwing this up, and maybe that item should be removed from the rest because it's not really hanging with all of these others. Under item statistics here, what it's showing is the this raw R is the, or R core. You're looking at the item total correlations. So if you look at the correlation between Descrim 101 and the score that was computed based on averaging across all four of these, so like their overall discrim factor score, what's the correlation between their individual variable score and the factor score that was computed. So once again, you would think that these should be, pretty highly correlated if it's a good, reliable scale. For checking out the others, let's look at if going back to look at what our things were. So looking here, SE 108, 109, and 110 makes the fourth factor. So let's check the reliability of that one. So again, we're just going to call those three variables. And now looking up at our alpha, we can see that 0.72 is, now we're in much better territory at least.
So you guys will do that for the other two as well. And I threw into the chat some guidelines for how to interpret alpha. Jake was the first one to respond, and he said in psychology we want alpha at least to be above 0.7, and he's absolutely correct. 0.7 is kind of our minimum adequate alpha. 0.8 we consider, 0.8 and above we consider good, and 0.9 and above we consider excellent in terms of internal consistency reliability. So even though we have a component or a factor that has those discrimination items, the alpha for that factor or component is still pretty shitty. So it's not a great unidimensional kind of score here or factor. We could calculate a factor score and use it in future analyses, or we could say, these items, for whatever reason, maybe it's because middle schoolers were answering them, maybe it's because there's low variability in answers, they're just not really hanging together well. And one person asked, would that, Josh, I think, is collective light team today, he asked if we should report it as a limitation, and you can. You may also just not use discrimination as like a single, like a composite score with such a shitty alpha. As Austin pointed out, even if we had removed individual items, the alpha wouldn't have gotten better. So it doesn't seem like it's measuring like one thing, that discrimination of economic opportunity or economic equality is the same here. We're probably not justified in using discrim as a single scale score or a single test score with our data.
Does anyone have any questions? That wraps up the entirety of this lab. So any Elise is asking if we should remove SE 108 since it improves reliability. Really it's a judgment call, but in this case I would say no, you wouldn't, because you don't want to remove variables unless you have to. And in this case, like, sure, your reliability goes from 0.72 to 0.78, but is that really something that justifies pulling that out? I'd say no. Like, you're still above 0.7, you're still good. Now if it's something that your reliability is unacceptable and removing something makes it acceptable, or if you have a major change, then okay, yeah, now you've got some justifications. But in this case, you wouldn't want to take that out just to increase your alpha by 0.06.
So Nia also asked if we would do this analysis, and I'm assuming this analysis you mean our Cronbach alphas after we do our EFA. The answer to that is it depends. Oftentimes an EFA is done in route to something else, so usually it's part of scale development. If you're trying to create a new measure for something, You write a bunch of items, or you have a bunch of tasks, or whatever it is that you're doing. You give it to a bunch of people, and then you do this analysis to see if you can reduce the large number of items to a smaller number of components or factors. If the goal usually is then to use those factors or components for future analyses. Like, it's not usually the end goal to say, oh, look, I can measure working memory. You usually then want to say, and I can use working memory in order to predict other things about a person. So because you want to be able to use your factors or your components for future analyses, then we would typically want to know, are they internally consistent or internally reliable? So not necessarily the case that you're going to see alphas computed, but it's often the case. And if you do a second critique and you do it on an EFA or PCA paper, it's not unusual to see them report alphas at the end of it. Oh, cool. We got some great advice from Morgan.
Yeah, so Morgan's talking about over here, and the Command Control Shift O, and also there's this button right here that is your outline. And so the reason that those, at the beginning of the semester I talked about, it gives you these collapsible things. It also puts it over here in your outline, and whatever you put here. So if we said change this to PSYC alpha, it'll, so you can quickly jump between different problems and stuff over here in this outline, which again is this button right here in the top corner.
Okay, so are we ready to transition now to talk about path analysis?